All right, let's jump right in. Today we're looking at two really powerful but totally different ways that machines learn to find patterns. So, one way is to literally try and build a brain, copying the messy, complicated wiring of our own neurons. The other way, it's all about drawing the perfect line, a masterclass in pure, clean geometry. Let's see how these two philosophies tackle the same chaotic world. So, here's what we're going to cover. First, we'll start small with a single artificial neuron, the idea that was sparked by biology. Then we'll see how you link these together to create powerful networks that can actually learn something. After that, we're going to switch gears completely and talk about a different approach, finding the perfect dividing line. That's something called an SVM. And finally, we'll see how both of these methods deal with the messy, real-world problems that don't have easy answers. Okay, first up, let's go back to the blueprint for all of this, the biological neuron. It's the tiny little piece that makes all intelligence possible, and really getting a handle on it is the key to understanding how we even started to build these things out of code in the first place. This is what's so cool. Look at the direct parallel here. On the left, you've got the real deal, a biological neuron, and on the right, you've got its digital twin. We've basically just created a mathematical translation for biology. The signals a neuron gets, that's just numerical data. And the strength of a connection, a synapse, well, that's just a number we call a weight. This simple translation is what lets us start building a digital brain. And this simple little guy, this mathematical model, has a name, the perceptron. Think of it as the foundational atom of a digital brain. It's not conscious, it's not thinking, but it can do one thing really, really well. Make a simple yes or no decision based on the information it's given. So how does this little atom actually work? Well, it's basically a simple three-step process. First, it gets its inputs, just a bunch of numbers. Second, it does some quick math, multiplying each input by its weight to figure out how important it is and adds them all up. And third, something called an activation function makes the final call. Does it fire a signal or does it stay quiet? It's simple, but as you're about to see, it gets incredibly powerful when you start connecting them together. Okay, so a single neuron, it's not going to win any awards for intelligence. The real magic, the part that feels like intelligence, happens when we connect thousands or even millions of them into a network. But just having a network isn't enough. The really crucial part is figuring out how to teach it to learn. And we build this network by stacking these neurons in layers. It's kind of like an assembly line for information. The raw data goes into the input layer. Then it gets passed through one or more hidden layers. This is where the really complex pattern matching happens. And finally, the output layer gives us the result. As the information flows through this web, it gets transformed, allowing the network to spot patterns that would be totally invisible to just one neuron. Right? This is the big question, isn't it? A network is just a bunch of connections. It's dumb. For it to be useful, it needs a way to get better, to adapt, to actually learn from what it sees. So, how do we give it that power? And the answer is this absolutely brilliant algorithm called backpropagation. Honestly, you can just think of it as a super smart way of learning from your screw-ups. The network makes a guess, it looks at the right answer, it sees how far off it was, and then it sends that error message backwards through the whole network to tweak the connections. This all creates this amazing learning loop. Okay, so think of it like this. Data goes forward, and the network makes a guess. Then we check how wrong that guess was. That's the error. Now the magic happens. That error travels backward through the network, and every single connection gets a little bit of the blame for the mistake. Then each connection is adjusted just a tiny bit to be better next time. Now, do that thousands or millions of times, and that network slowly but surely gets smart. All right, so that's one whole philosophy. Build a brain and teach it by correcting its mistakes. But what if we threw all that out? Let's totally switch gears from biology to pure geometry and talk about the support vector machine, or SVM. It's a completely different, and I have to say, beautifully elegant way to classify things. An SVM doesn't try to build a brain. It's not about neurons and synapses. It's about drawing a line. Its entire goal is to find the one, single, best boundary that separates two groups of data. And not just any boundary. It wants the one that creates the biggest possible gap between the two groups. Okay, to really get this, just imagine this map. You've got two groups of data, the blue dots and the red dots. You can see they're separate. The job is to teach a computer to tell them apart. So how would you do it? Well, the obvious first thought is you just draw a line between them, right? Easy. Problem solved. This line works. But wait, so does this line. And this one. And this one over here. In fact, There are a ton of lines, an infinite number, that could get the job done. So which one is the best? I mean, which one is going to be the most reliable? The one you can trust when a new piece of data comes along that you've never seen before.
And this is where the SVM is just brilliant. It doesn't just find any line. It looks for the one single line that creates the widest possible street, the biggest possible margin between the two groups. It's not just about separating them, it's about creating the biggest safety buffer. And that perfect boundary has a name, the maximum margin hyperplane.
And these points, the ones right on the edge of that street, they're the VIPs. They are called support vectors. Why? Because they are the only ones that matter. They're the critical data points that literally support and define the exact position of that perfect line. You could move any of the other dots around, and the line wouldn't change one bit. But if you move a support vector, the whole solution changes with it. Okay, that's all fine and dandy when you can draw a nice, clean, straight line. But the real world isn't that neat, is it? What happens when the data is all mixed up? What if a straight line just won't work? Well, this is where the SVM has one more amazing trick up its sleeve. I mean, look at this mess. You've got blue dots completely surrounded by a circle of red dots. There is no straight line anywhere on this flat surface that can cleanly separate these two groups. This is a non-linear problem, and frankly, this is what most data in the real world looks like. So, are we stuck? Nope, because the SVM solution is called the kernel trick, and it's all about changing your perspective. Instead of trying to draw some crazy, curvy line in our flat 2D world, the SVM uses a math function to project the data into a higher dimension, let's say a third dimension. And what's amazing is that from this new vantage point, what was all tangled up suddenly becomes easy to separate. You can just slice right through it with a simple flat plane. And here's the really mind-bending part. The trick is that the SVM doesn't actually have to do all the crazy math to move every point into that new dimension. The kernel function is like this incredible mathematical shortcut that lets it find that perfect separating plane without doing all the heavy computational lifting. It gets all the power of a complex, nonlinear boundary, but it only has to do the simple, efficient math of a straight line. So let's just recap, right? We've seen two completely different philosophies. On one side, you have neural networks. They're inspired by biology, and they learn by slowly tweaking this massive web of connections. The analogy is simple. You're building a brain. On the other side, you have support vector machines. They're inspired by pure geometry, and they work by finding one single perfect boundary. The analogy there? You're drawing the perfect line. And that really leaves us with this one big question. When you're trying to solve a new problem, do you build a complex, messy learning brain, or do you draw a single, elegant, perfect boundary? The thing is, one isn't better than the other. They just represent two deeply different ways of seeing a problem. And understanding which lens to look through, well, that's the first and maybe the most important step in teaching a machine how to think.